Hello and welcome to Lecture 3 of the Principle of Relativity in Phys 1104, and it's time to get a little more mathematical. What we're going to do in this lecture is take a bunch of the ideas we've seen in the previous two lectures and derive them with a little more mathematical rigor, and in the process we're going to get a whole bunch of other equations that we're going to find useful in problem solving. Let's start by thinking about you and Trogdor, and each of you has a set of axes. I'm going to call your axes A and Trogdor's axes B, or you can think of those as the names of your frames, and so there are origins OA and OB. And Trogdor is moving relative to you with some relative velocity VAB, right? That's the velocity of B relative to A. And initially, you're at the same location, so your origins coincide. And remember that a frame is also a clock along with the axes, and so you each have a clock, and as you pass by each other, you synchronize your clocks. So we're calling the time when you pass by each other t equals 0. And now Trogdor moves off to some other location. And let's say that at some moment, some event E occurs. What is an event? What do I mean? It's just anything which happens which has an identifiable location and time. So I've drawn it as something like a firecracker going off, but it could be anything where we can specify when it happened and where it happened. You and Trogdor can now make measurements of the position and time of that event. And what we're interested in is how Trogdor's measurements relate to yours. The first thing we're going to do is assume that your clocks stay synchronized. That seems reasonable, right? If you have good clocks, that once you've synchronized them, they should stay synchronized. But experiment actually tells us that this is not a good assumption. This doesn't agree with experiment. However, as long as Trogdor isn't moving too fast relative to you, where too fast means close to the speed of light, then this is a good approximation, and so we're going to use it. So that means any time you measure is going to be the same as the time that Trogdor measures, and so we can just drop our A and B subscripts and call it t. So the time of the event is just going to be t sub e. And now to think about how the positions relate, the key thing is to notice this vector RAB, which is just the position of Trogdor's origin relative to your origin. And if you just look at this trio of vectors, you can see that there is a vector addition going on there. And so the three vectors are related like this. The final thing is that we can think of how this RAB relates to Trogdor's velocity and the time. Well, clearly, RAB is just that velocity times TE, since at time 0 you were at the same location. And so we can just replace RAB in this equation like so. So we've got these equations now, and I'll just mention that that second equation is often solved for RBE and written this way in a lot of textbooks. That's fine, but I prefer this first version for reasons that I'll tell you in a bit. And, you know, there doesn't seem to be all that much to these, right? This is just saying that everybody measures the same t, and this really just came from a vector addition. Nevertheless, these have a name. They're called the Galilean transformation equations, named after this guy. And so what we're doing here is what is called Galilean relativity, although this guy's pretty responsible for it as well, but he's got so many things named after him. Let's give this one to Galileo. Now, when you saw the title of this unit, you might have hoped, or at least thought, that we would be doing stuff by this guy, and I wish we could, but we just don't have time, and I'll just briefly mention it. So, the big thing about Galilean relativity that turns out not to be consistent with experiment is this clock staying synchronized. And what replaces that in Einstein's special relativity is that all observers agree on the speed of light. That ends up leading to a very different set of transformation equations that we call the Lorentz transformation equations, which is more consistent with experiment. But the good news is that for observers at low relative speeds, so in the limit as v goes to 0, these reduce to the Galilean transformation equations. Let's move on from how positions transform to look at how velocities transform, which will allow us to reproduce what we had in the previous lectures. And so we need to track something that's moving. So instead of you and Trogdor observing an event, you're now observing some moving object, and you want to keep track of where that object is. So, of course, you each measure its position, and we already know how the position you measure and the position that Trogdor measures at, say, this initial time are related. And now, at some later time, relative to you, the object and Trogdor have both moved. We could, of course, look from Trogdor's point of view, too. First thing to notice is that there are a heck of a lot of vectors on this diagram, and it's getting a little confusing. So this is actually one of the few cases where just doing the math is a little easier than looking at the picture. So that's what I'm going to do. But before I do, I'm going to show you where we're going in the diagram. If you look at, in this diagram, how the object's displacement looks to you, the object has gone straight to the right. But if you think about what Trogdor must have seen, then you can see that the object relative to Trogdor has moved a little left and a fair bit down. And so clearly the observers don't agree on the displacement vector, and so what we're going to have to find is what the transformation is between those displacement vectors. So here's the diagram to help you tell what the symbols mean, and let's just do the math. Here is the displacement of the object relative to you, and that's just the usual definition of a displacement, a final position minus an initial position. And what I'm now going to do is I'm just going to use this relation to replace each of these with expressions in terms of positions as measured by Trogdor. So I'm going to have the displacement relative to you, and it's now going to be equal to, and so this part is going to turn into and this is all going to be minus all the same stuff initially. Now look at what we've got. If I just collect the RABs, I'm going to have RABF minus RABI. Well, that's just delta RAB. And then collecting the BOs, I'm again going to have RBOF minus RBOI, and that is just delta RBO. And so there is our transformation relation for the displacements. Now what? Well, we really want the velocity transformation, but I'm going to claim that's easy, because what we do now is we just divide by delta t. This isn't yet what we want, because this will give us average velocities, and we just want velocities, right? Or instantaneous velocities, if you want to call them that. We're almost there, because all we have to do now is take the limit as delta t goes to 0 of both sides. And now by definition, this is VAO, and this is VAB, and this is VBO. And we've just recovered the equation that we were using repeatedly all through the last lecture. We've got our transformation equations for positions, displacements, and velocities. The logical next thing to do is get our transformation equation for accelerations. And so we're going to need to do delta v's, right? So here's your change in the change in velocity of object O relative to u. And again, I'm going to rewrite it in terms of velocities relative to Trogdor. So I'm going to do exactly the same thing. I'm just going to replace this, and I'm going to use the velocity transformation equation. And then I'm going to do the same thing with this part. And we see something fairly familiar happen from the last lecture. Note that there is VABF and VABI, except Trogdor is moving relative to you at a constant velocity. And so I don't need the F and the I. That's just VAB. And so because of this minus, those are just going to cancel each other out. And all we're going to wind up with is, and that is just delta V relative to Trogdor. Oh, delta v relative to Trogdor is just the same as delta v relative to u. That's nice and simple. So if we now want the accelerations, we'll do the same trick we just did. We will just divide both sides by delta t. And then again, just take the limit as delta t goes to 0 of both sides. And I'll remind you that what that means is the derivative, that is by definition the acceleration. And so the acceleration in one frame is the same as the acceleration in the other. These are the relations we've now got. This first one is one of the Galilean transformation equations, and from that we got these two relations. And in particular, this one I used repeatedly all through lecture 2 of this unit. And if you look back, you'll actually see I rather sneakily used this one in lecture 1 when I was talking non-inertial frames and what Sam would see on an accelerating cart. So now we've actually got justification for them, and I'm just going to finish up by pointing out some nice things about these. So this has a form that makes it easy to remember. Now, I'm still not advocating that you memorize it. However, I'll point out that there's this nice thing that you can think of it as if these b's that are on the inside here sort of cancel out, and this now collapses down, right? These r's somehow combine to give you this RAO, right? And so that's why you can think of this that way. This one has the same structure, right? And you can think of the b's in here as sort of canceling out to give you that. And the one remaining thing I'll point out is that, let's say this is U, A, and here is someone else, B, so that there is a position vector that we would call RAB, right? The position of B relative to A. And if you think of what the position of A relative to B is, like so, it's clear that just RAB is negative RBA. And similarly now, if you just take the derivative of both sides, the time derivative of both sides, then all you end up with is that VAB is negative VBA, which we've actually used a bunch of times right from the first few minutes of this unit. So now we've got all these justified.